So now a city has 10 intersections. So imagine this is the city. I didn't draw the 10 intersections, but assume this is the city. Some of the intersection will have a traffic light, something like this. And then some of those that with a traffic light will have a gas station next to it. So let's say this question, how many ways of this can happen? Okay, this question, if you did not grow a tree in your brain, you don't know how to solve it. So, how to solve it? You grow a tree in your brain. Start with nothing. What is the question? You have 10 intersections. Some will get traffic light, that means some will get nothing. So, some will get nothing. Okay, nothing. I write empty set. Okay. And then some will get traffic light, right? And then here, some of those who get traffic light will also get a gas station. That means it's possible. Some only get a traffic light, and then some get both traffic light and gas station. So that means you have this tree, traffic light, and you get traffic light and gas station. I just call it G. So that means what? This is the first crossing. There are what? 10 intersections. So you branch this for the second intersection. So you branch this. Now you have what? The second intersection. What? You branch this again. You have the third intersection. So how many branches we have? 3. How many times we branch? 10 times. So the answer is 3 to the power 10. That's it. Let me recap. You have 10 intersections. Imagine something that looks like this. Some have traffic light. Those with traffic light, some of them have a gas station. How many ways are possible? That means what? You can have nothing, only traffic light and gas station. So grow a tree in your brain, branch with 3 branches. Every time when you move, it means you move from intersection 1 to intersection 2 to intersection 3. How many times you move? 10 times. What is this? Cartesian product of these 3 sets 10 times. So that's why you have this. So permutation. What I did yesterday is that permutation is this pi thing. What is this pi thing? Just put I in J. That's it. So this is just a fancy symbol. In some other books or other people use sigma. It doesn't matter. You can draw a chicken, you can draw a duck here. It doesn't matter. Okay. So this is just simple. And then what I talked about yesterday, there are 2 numbers, cardinal and ordinal. So you can think of it like this. The ordinal is like the order. So 1, 2, 3, 1, 2, 3. So you have red number. Red 1, 2, 3 and the black 1, 2, 3 are different things. Okay? And then you also have the green 3. What is the green 3? Green 3 is how many things here? If I see this as a set, there are 3 things. If I see this as a set, I also have 3 things. So that means what? That means there are actually 3 kinds of things. The first is the index or the order or the location. Or if you talk about programming, it's called pointer or address or memory location. Okay, so many names. So 1, 2, 3, 1, 2, 3 is like address where you live. Think of this as houses. And then people swap houses due to some reason. So this is permutation. The content inside the houses and the address of the houses are not the same thing. And then how many houses? The green 3. So these 3 numbers are different meaning. Different meaning. The red one is called ordinal. The green one is called cardinal. The black one is the content. We just care about the green thing or the red thing. And then what the heck is this? Pi, I just said that. Pi is just pi ij means what? Put I to j. Okay. Then what is this? This is saying that all the possible way you can make a permutation. Of course, for those who learn permutation in high school, you say, isn't that just 3 factorial? Yeah, but I'm explaining what the heck is 3 factorial. You know what is 3 factorial? Good, but you are just remembering a formula. Remember a formula, that means you are no different from ChatGPT. And ChatGPT remember 10 times, 1,000 times better than you. So that's why you need to understand things. Very recently, Apple just said that ChatGPT have no intelligence. So that's good news. Just to let you know. For those who don't know computer science or AI, they will say, oh, ChatGPT very powerful, a Terminator coming, a human will die. Bullshit, no. The more you study computer science, the more you understand the computer is dumb as fuck. So therefore, AI kill human? No. Go back to here. What is this sim 3? It's just some fancy symbol to scare people. The meaning is that you have 3 stuff, 1, 2, 3. Again, this 1, 2, 3 can be anything. 1, 2, 3 is just a symbol. It's just a dummy variable. It's just a thing. I name it as a 1, I name it as a 2, I name it as a 3. I can call it ABC. I can call it chicken, dog, and cat, something like that. So this thing means if I have 3 stuff, what are all the possible permutations are there? These are all the possible permutations. And I list all these possible permutations to a bigger set. Let me recap. Each of these small bracket is a set, and each of these small sets have all the same free thing. So free thing here, 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 free thing here. Okay. So all the small set, if I put 2 bar, cardinality is free. But what is permutation? Permutation asking how big is this big bracket? That's the idea. So therefore, what is permutation? Permutation means, okay, if you remember, I said you should draw a tree whenever you think. So draw a tree for this question. I said draw a tree in your brain. Draw a tree in your brain. This is the mental image you need to think every time when you have Cartesian product or draw a tree. What about permutation? Every time when you talk about permutation, please have a mental image in your brain that you are not talking about the original set. The original set is S. Now I said it's sim-free. Just a fancy symbol. You can draw a chicken here, doesn't matter. Okay? We are talking about a bigger set. This is what? This is a set. This is what? This is a set of sets. You can think of it as a bigger set. Okay? So whenever we talk about permutation, combination, permutation with repetition, combination with repetition, we are talking about something bigger. And you need to have a mental image on how the heck this is formed. So what's permutation? Now I'm going to talk about this. So if I have 3 elements, 1 and 2 and 3, how do we form permutation? Again, draw a tree. You have, first of all, when you draw a tree, you need to know how many things you can branch. Well, you can do the following. Do nothing. Do nothing means empty set. Then what? You swap 2 things, right? So swap 2 things. And then what? You swap 3 things. You see, this is also a tree. So do nothing means I have 1, 2, 3. Swap 2 things, you can what? Swap with respect to 1, swap with respect to 2, swap with respect to 3. So here you have another branches. Swap 1 swap with question mark. That means I didn't specify what the heck is it. 2 swap with question mark. 2 swap with something else. 3 swap with question mark. What about swap 3 thing? Well, then all the things in 1, 2, 3 have to change their location. So in this case, I draw a cycle. I draw something like this. So this is what? 1, 2, 3. This corresponds to I do nothing. I swap 1, right? How many other guys are there? 3 things, but I have to swap 1. So I only have 2 choices. So here I can have what? 1 swap with 2 and 1 swap with 3. So this one gives me what? 3 does not move, so 3 is fixed. So 1 swap with 2, so these 2 change location, so 2, 1. This means 1 swap with 3, so 2 does not move. So I swap 3, 2, 1. Okay. Now for this 2, I can do the same thing. I swap with 1 and I swap with 3. So for this case, 3 does not move. For this case, 1 does not move. You will see some of them repeat. Okay, and then what? For when you swap 3, you can swap 1 and swap 2, right? Okay, and lastly, you swap everything. You have 3 boxes. You do not allow any box stay in their original location, so you either go like this or you go like this. So 1, 2, 3 become 1, 2, 3, and then you imagine go back to here, or 1, 2, 3, and then you go back to here. So you either have 2, 3, 1 or 3, 1, 2. Of course, you can keep going on. So I just draw here. So I'm not saying this is everything you need to do. I'm just telling you this is the mental picture. So if you have 1, 2, 3, you swap 1 thing. No, swap nothing. Swap a pair. Swap 3 things. This means do nothing. So 1, 2, 3, nothing. This means you swap 1 pair. So you either swap starting with 1, starting with 2, starting with 3. Then once you have finished, okay, I'm now focusing swapping with 1. Then I look at the remaining thing. I can either swap with 2 and swap with 3. So I have this. So this is a tree. And this gives you a very systematic thinking. You will never miss the stuff. Okay, what about 3 things? So here I will have other tree. I just didn't draw the full tree. Swap 3 things you can think of. Now I have 3 things, right? You can think of this as like I swap 2 things. And then you copy this tree inside. Then you will get another big tree. This is what? This is the 3 set, 4 set, the inclusion, exclusion principle. So what I mean? You first build a basic case. And then you go to a bigger case. Whenever you go upward, you always look backward to see whether or not something can put inside. This thing is exactly what? This thing is exactly what we do here. This thing is also exactly what we do here. And now this up here again. And of course, people know 3 stuff. How many permutations? 3 factorial. Yes, that's 3 factorial. Yeah, 3 factorial. I know you know. But I'm talking about this is important. Grow a tree in your brain. Okay. Then what about 4 things? Suddenly you have some beautiful picture. First of all, don't worry. I'm not going to test you this picture. You have 1, 2, 3, 4, 2, 3, 4, 1, and blah, blah, blah. So let's look at the red arrow. So 1, 2, 3, 4, 4, 1, 2, 3. This means what? You can think of this. I have 4 boxes. So 4, 3, 2, 1, I move to here. Okay, so it's either move here or move here. And then what about this? Well, it's the same. I move here. So this means I move here. All the red arrow means I move here. Okay, so each arrow has a meaning. First of all, this thing is called a graph. What's a graph? These are numbers. You think of it as a point. Then arrow means you can get this point from this point. You can get this point from this point. And then the arrow means you can go from a starting point to an ending point. That's the meaning. And then this graph means what? Can I move from 1, 2, 3, 4 to 2, 1, 3, 4? So let's say I want to start at here. Can I reach here? So let's see. Okay, I go to here. This arrow means I can go to here. And then this arrow means I can go to here. And then this arrow means I can go to here. Okay, I want to reach here, right? So I can go to here. And I can go to here. Oh, the answer is yes. But also I can say from here, I go to 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 here. And I can keep going. Here's a higher level overview. Why counting is so hard? Because every time when you think about counting, you're only thinking about one particular path here. But turns out this picture have more than one path. You can go from here to here. Why people make mistake? Because people didn't think about all the possible way from this node to this node. You miss some of the possible path. Then that's the root reason why people make mistakes. And this thing is intrinsic in all the permutation, combination, all the thing. So this is a reason why this kind of thing is hard. Because it's impossible that you always never miss one particular path. It's impossible. So that's why this thing is hard. And then what about 5 things? Okay, you go to this Wikipedia page, you can look for 5, 6, 7, and then you see lots of beautiful pictures. These 2 slides, what's the purpose? Explaining what the heck is in the back of permutation. What's the formula? Oh, so easy. It's just k factorial. What's k factorial? You see, I define it like this. You may write, oh, k factorial is k times k minus 1 times k minus 2 times, something like this, right? Yes, that's correct. But you forget recursion. This means what? This means, how do I define a thing? I define a thing by the previous case. Then, let's say I want to know what is 7 factorial. What I do? Go look at here. It's 7, that means the k larger than 0. Yes. So it will be what? 7 times 6 factorial. At this moment, you should not jump out and say, oh, I know 6 factorial, 6, 5, 4, 3, 2, 1. No. You should say, okay, now I see 6 factorial. I come back to here. It means 6 times 5 factorial. And then, okay, I see 5 factorial. Come back to here. It gives me 5 times 4 factorial. Directly jumping to this conclusion does not show you understand what is recursion. So, mathematically, I said, combinatorics in exam, usually the answer is just number 10, 25. But how do you come up with this number? It takes you half hour sitting in the exam hall and then you don't know how to come up with a number. Okay? And then, just let you know some funny thing. What about if this is very big? This is not in exam, I just let you know. Okay? So, this is called Stirling formula. What does it mean? It means, okay, suppose I have 2000 factorial. How do I calculate it? You plug in the 2000 in this n. It will be 2 pi times n. 2000, 2000, and 2000 divided by natural log e. Okay, so this gives you approximately the value of 2000 factorial. This is approximation, this is not equation. And then, just for fun, what is this? Yeah, just for fun, not going to tell you why. And also, you can actually have half factorial or 0.5 factorial. This is in the gray thing. You go to Wikipedia or Google yourself, okay? So just for fun. So now, once you know this, now here's come the first difficult thing. How many permutations are there for the English word happy? You have 2 things that are the same. They repeat. So what's the approach? You first treat them as different things. So now you have H-A-P-P-Y, but this P I call P1, this P I call it P2, and P1, P2 are different things. Now they are different things. Different thing means I can treat it as a permutation. Permutation means all the things are different. So 5 things, 5 factorial. So 5 times 4 times 3 times 2 times 1. Although I said you should have this and then this, okay, and then this. But in calculation, you are allowed to directly jump to conclusion. This is understanding, this is calculation. They are different things, okay? So you have 120. But the idea is P1 and P2 are the same thing. We just could give a label. So we actually double count the following. For example, this happy and this happy are the same thing. I just swap these 2. But if you go back to the original problem, these 2P, there's no label. So that means we cannot tell which one is the first one, which one is the second one. So that means we actually double count something. So that means among all these 120, we double count something. So we divide how many we double count. In this case, it's really double count, it's 2. So therefore, 60. So the idea is, if I have permutation with possible non-distinct object. That means I have something like this. They repeat. What's the number of permutation? Now it's not n factorial. It's n factorial divided by how many things each of the things that repeat. So in this case, H do not repeat, A do not repeat, P repeat, Y do not repeat. So P repeat, right? So we put a 2 here. Even more general, you can think of it like this. How many H there? 1. So you have a number of H here. How many A here? 1. How many P there? 2. How many Y there? 1. If I treat this 5 thing as distinct object, how many things here? 5. Which is this thing, because 1 factorial is 1. So therefore, if you allow repetition, how do you think about this thing? You think of it as permutation. By first adding additional label. You treat them differently. Then you apply permutation, factorial. After you finish this step, you go back to say, oh, this is additional thing I introduced. They shouldn't exist in the beginning. I cancel it out. So this is the idea. This kind of thinking is totally the same as what? As you have a function, and then suddenly you create a 3 divided by a 3. This is multiplying 1. You can always do that. And this 3 somehow simplify the stuff. So in this case, I'm doing something similar to this. So now, this is another example. Suppose I have 1, 1, 2, 3, 4, or A, B, C, D. Okay? So how many ways to permute this? Again, first, you treat them as different things. So we have 1A, 1B, 2, 3, 4. So you treat these two 1, which we cannot tell which is which, but we label them. Then how many ways can you permute this? 5 factorial. 5 factorial. But among this number of factorial, there are some of them are double counted. For example, these 2 are the same thing because you have no way to tell which is which, right? So therefore, we have to divide by how many possible ways we double count. So now we have 1A and 1B. So how many possible permutation here? 2. So that's why we divide by 2 factorial. What about the 2, 3, 4? They both exist alone. So they are all 1 factorial. So divide by 1 factorial is the same as we don't write it down. So therefore, this is the answer. Okay? Now, what about this? I have 1, 1, 1, 2, 3. 1, 1, 1, 2, 3. The 1 repeated 3 times. So first step, I treat them as different things. So I have 1A, 1B, 1C. So they are not the same thing. How many things here? 5 things. 5 factorial. Okay? But now for 1, 1, 1, these 6 things are the same. Why? Why there are 6 things? Because there are 3 things. How many permutations inside these 3 things? 3 factorial, which is 6. So these are all the 6 possible 1, 1, 1, 2, 3. Here, there's no ABC. That's why if I look from an outsider point of view, these are all 1, 1, 1, 2, 3. But if I add a label, these are different things. But I don't know which is which. So I have double counted 6 times. So that's why I need to divide by 6, which is 3 factorial. What about 1, 1, 1, 2, 2? So now you add label. 1 ABC, 2 AB. How many stuff here? 5 factorial. But we overcount so many things. How many things? All the possible permutation in 1 and all the possible permutation in 2, and they also mix them up. Therefore, we have this number of 1, 1, 1, 2, 2. So from outsider, these are all 1, 1, 1, 2, 2. But you add label, so here are different, but from outsider, they can't see the difference. So you have double count up this many. How many? These have 3, these have 2. Cartesian product, 12. You have P set, and you have a Q set. The P set is this 3, 1. Q set, you have 2 number 2. So how many ways is the cardinality here? Remember, Cartesian product is the number of way here times number of way here, so which is 3 factorial and 2 factorial, so that's why it's 12. So that's why you have this. And in this particular case, it will be what? It will be this formula. How many total object? 5. How many type 1 repeated object? 3. How many type 2 repeated object? 2. So you have this thing. So that's why this is a formula. So what is this? The top is permutation. The thing in bottom is number of repeated object. And let me tell you, magically this is multinomial coefficient. You haven't even learned binomial coefficient. That means suppose you don't know what's binomial coefficient, you actually learn multinomial coefficient earlier than binomial coefficient. 3x plus 4y minus 7z plus 9w minus 11q power 7. How do you expand this? You will have a multinomial coefficient, let's say power Okay, 7, and then 1, 2, 3, 4, 5. You have 5 number here. Then what is this thing? This thing. And then you will have 3x power this number, and then 4y power this number, and then 7z power this number, and so on. And this is how you expand anything as big as you want. Don't worry, we will see this later. Multinomial coefficient. And it actually is what? Permutation with repeated object. So this is the first thing. Now I have another example. Previously, all this 1, 1, 1, 2, 2, the repeated thing, they stick together. So the 1, 1 stick together, the 1, 1 stick together, and the happy, the p stick together. Okay, now suppose I have a simple example. How many possible permutations are there for baby? So the b repeated, but they don't stick together. It's the same. So how many b? There are 2 b. How many a only occurs once? How many y only occur once? So b is called type 1, a is called type 2, y is called type 3. So r means how many types? So you have 3 types of thing, which is b, a, y. And for b, you have 2. For a, you have 1. For y, you have 1. So you have R3. So you have 3 things in the denominator. And each of the number n1, n2 up to nr is actually how many things for each type. And what's the thing on top? Total number of stuff. You have 4 stuff. So 4 factorial divided by 2 factorial divided by 1, 1, which gives you 12. And this is also what? Suppose I have x plus y plus z plus w power 4. Okay, that means there will be a term. The power will be 12x squared y w z. Yes, and this guy is exactly what? 4211. Sorry, 42. So there should be 4 numbers. So there will be 1. This is 0. Okay. Yes, that means if I have x plus y plus z plus w power 4, I expand it. And for some reason, I want a term that x is squared, y is 1, z is 1, w is 0. What's the coefficient next to the term? It will be 12. And this is how we expand power 4. This is multinomial expansion, okay? But now we're talking about permutation. Here's another example. So this formula, what? It's just factorial divided by factorial. And it has a fancy name called what? Division rule. But it doesn't matter. So suppose I have 10 chess players. And then, let's say in the chess, there are 4 from Russia, 3 from US, 2 from UK, 1 from Brazil. Usually these are the places that the people are very good at chess, okay? And then they fight with each other. Then in the end, somebody will win, somebody will lose, right? I'm saying, if I, in the end, list a bunch of order the list, that means it's like Olympic. You have a list, okay? You have a list, and then who is number 1, who is number 2, who is number 3, who is number 4, who is number 5. And now let's say we don't care about who they are, we care about what country they're from. Then we have a list of what? Of flags. And this is an what? A permutation, right? Now I'm asking, how many possible permutations are there? So important, because let's say the Russians are very good. So Russia take all the first 4 positions. But if we talk about flag, we don't care which is the first one. But if we talk about person, maybe this person K and this person D are different things. So this is one permutation, this is another permutation. So now I'm saying we talk about flag or country. So that means we're talking about, we don't care about the person, we care about this. So that's why this is this one. So how do you count it? 10 completed y, 10. 4 from Russia y, 4 factorial. 3 from US y, 3 factorial. 2 factorial and 1 factorial. So this. So this is this number. So that means if you have 10 people in a competition, this will be all the possible number of ways you can arrange their ranking, but ignore who they are, just care about the flag or nationality. Okay? And this thing have nothing different from this. Same for baby, happy. Alright? And then gray means not in exam. So what I talk about is permutation and permutation with repetition. And this is a very special permutation. It's called derangement. It means you do permutation. These are all the permutation 1, 2, 3, 4. But all the boxes must move. So that is, for example, I have 4 boxes. Okay, 1, 2, 3, 4. Permutation, okay, you can now know is a swap or cycle. So suppose I swap these 2, then I have 2, 1, 3, 4. This is not allowed in derangement because these 2 doesn't move. So everything must move. Then this is a new thing called derangement. I'm not going to have this in exam. I just let you know this thing exists. Okay, this thing is a subset of this. What is this? This is sim 4, symmetric group 4, and all the red are all the possible derangement. Then you will wonder, how do you count how many things are there? Actually, you do something called inclusion-exclusion principle. Actually, it's this. And then, after doing that, you have a funny formula that looks like this. You put a factorial symbol before the number, You pronounce it a factorial 4. You don't call it 4 factorial. What is the definition? Here's an example. A factorial 4 is 4 factorial times this funny expression. You can think of this as 1 divided by 0 factorial. So you have starting with 0, and then you have 1, 2, 3, 4, 5 factorial, but you flip the plus and minus until the end, until your number. And this thing always is integer. So this is the formula. This will give you what? The number of derangement for n object. How do you prove this? Actually, this is inclusion-exclusion principle. So this is a new thing. Again, this is not exam. I just let you know this kind of thing exists. Okay. Same for the Stirling approximation. I just let you know that kind of thing exists. Okay. I'm not going to test you. And also this, I'm not going to test you why infinity factorial is 2 square root 2 pi. I just let you know this kind of thing exists. Okay. And if this module is not in computer science but in the mathematical department, then I will ask you this in exam. But we are not. After we talk about permutation, now combination. And combination and permutation very easy. I always use this example. I like this example a lot. So suppose I have to fight 3 people: Elon Musk, Joe Biden, and Mike Tyson. Permutation means order is not the same. Combination means order is the same. So for example, if I fight Mike Tyson first, and then I fight Elon Musk, and then I fight Joe Biden, it's not the same as I fight Joe Biden, Elon Musk, Mike Tyson. Why? Because if I first Mike Tyson, I die. But if I first fight Joe Biden die. Then what about combination? Combination is I'm doing 1 versus 3. In the boxing arena, they all appear at the same time. So that means this is like I fight them 1 by 1. This is like I fight the total fighting power of them at the same time. So they fight me at the same time. So this is a very funny example. And because this is funny, so you have a strong impression of remembering this. And different people have different preference. Some people may have even better story. So here's a technique. Sometimes you want to remember some math concept, and the math concept is so difficult to remember. Make up some story. The point is, it's not about make up a meaningful story or a reasonable story or a sane story. You can make up some crazy story. Like here, I'm going to kill Joe Biden. So this is crazy story. But because this story is crazy, it stores more in your brain. So this is how you remember permutation and combination. Combination means order doesn't matter. Permutation means order matter. So what is this? So suppose I have 5 people, and then I form 3 committee. So this is combination. This black thing is permutation. Combination means 1, 2, 3, and 3, 2, 1 are the same thing. I don't care about the order. But for permutation, I care about the order. And this picture also shows you one thing. Combination is a subset of permutation. Okay? And it's also a proper subset. So I have a combination, I call it C. Permutation, I call it P. Proper subset means it's not equal. Okay? Well, it's equal if they only have 1 element, or 2 elements, or nothing. Nothing is all, the permutation and combination of nothing is also the same. Okay? But anyway, so this gives you a hint. If you count some number, you will probably sometimes confuse, should I use combination or should I use a permutation? But this figure shows you that the number of combination is much smaller than the number of permutation. So let's say you do some exercise or in exam or whatever thing, you count something, and if you somehow feel that, the number I obtained is much larger than what I'm supposed to get, this gives you a hint. You mix up combination and permutation. This is for 5. This picture, if you have 10, let's say 10 people choose 3, then this you can imagine you have an even bigger table, and this bunch of things are not considered in combination. So the difference in the magnitude, the number, is even bigger. So if you somehow calculate some number and you feel that, it doesn't look right, it's given a hint, you mix up these 2. Now we enter binomial coefficient. 5 choose 3. Okay, some people will write this. Okay, we don't write this. We just write bracket. Okay, because later we will have this bracket. You have this bracket. You have this bracket. They are all different things. This is 5 choose 3. So you write n choose k in this form, and then it's defined as n factorial divided by k factorial, and then n minus k factorial. This is just definition. Okay, so 5 choose 3 is 5 fact divided by 5 minus 3, so 2 fact, and then 3 fact, and then you have this, and then it's 10. Same for 4, 2. So what the heck is this number? It means n choose k. So 5 choose 3 means number of ways you form a k set, that means 3 set in an n set. This is 5 choose 3. So all the red have 3 person, and the whole row have 5 person. So this is all the possible combination you can get. 3 person from 5 person. You don't care about order. These are order. So this is the Mike Tyson, Joe Biden thing. This is not, okay? So this is the first meaning. Second meaning, it is also the number of string with length n with exactly k1. So what the heck is this? This is a length 5 string. Length 5 string, I have 3 ones, right? So this is one particular case. I can have 3 ones in this length 5 string. But I can move this one later, right? So I have another string. If I want to put 3 ones, insert it in 5 boxes, and all of them contain 1 for 3 boxes, how many way are there? It's also this number. Number 3, this is the one probably you learned in high school. It is the coefficient x, k, y, n minus k in binomial expansion. Okay, number 4 is also this. These are binomial coefficients. These are also binomial coefficients. What is this? This is inclusion-exclusion principle. There's nothing n choose k. There's no multiplication. You are just talking about sets. You don't even need to have factorial to get binomial coefficient. These are binomial coefficients. They're the same thing. And there are 5th thing, 6th thing, 7th thing, 8th thing, 9th thing. I just stop here. What I'm talking about is that there are actually many meanings for this number. And this number, because it has many meanings, and sometimes you forget one of the meaning, you don't know how to solve a particular problem. It's because you are not aware of that meaning. And this, I just said, nk larger than 0. It is possible you have negative. And I just let you know, it is possible you put a half, negative 3. Then this is called general binomial coefficient. Again, not in exam. I just let you know this exists. Okay, let's say, okay, it's a power 3, 3a squared b, 3ab squared plus b power 3, right? So this number, this is a 1, this is a 1, okay? These come from here. My point is, this number is what? 3a squared b, 3ab squared. You can think of it as, I have three ways to form a combination of object type 1a appear 2 times, object type 2 appear 1 time. If I want to find some combination, object 1 type 1 appear 1 time, object 2 appear 2 times, I'm looking at this number. So therefore, this kind of number actually tell you some method to count stuff. And here are even more crazy property. So if I write this triangle, and then I name a row, and I name like this, I draw this red line, and I sum all the number, it gives me Fibonacci sequence. And this is the triangle, okay? I said this figure tells many things. For example, the first number and the last number are always the same. And they are mirror image. So this mathematically means this page. First, n choose 0 and n choose s in 1. What does it mean? You pick nothing. How many ways can you pick nothing? 1 way. You pick everything. Only 1 way you pick everything. 1. What is this? Symmetry or mirror image. This 8, there's 8 here. This 8 and this 8 come from this and this. So 8 choose 1 and 8 choose 7 are the same. What about this? Sum of n row. Sum this row. Okay, this is Fibonacci sequence. Sum this row horizontally, 1. Sum this row, 2. Sum this row, 4. Sum this row, 8. 1, 2, 4, 8. Okay, next is 16, 32, 2 to the power something. So this is what you see. And then this is sum rule. What the heck? I consider this triangle. 1 plus 5 give you 6. Let's say this. 3 plus 3 give you 6. 21 plus 7 give you 28. That means any number in this form, the top 2 add up give you the thing in the bottom. And mathematically, you write something like this. And actually, we will prove this. And lastly, this is the Fibonacci sequence. That is, you add number in the red. So you have even more. In the very last page of this slide, I will tell you how the heck you know this. How the heck you can come up with this. That is, this is additional thing. Suppose I have a summation, k factorial n choose k. What is this? From 0 to 5,000. Can you have a way to find this? There is a way to find this. Therefore, that means what? You don't need to remember this formula. If you know how to calculate this, you can KO all this thing. Yeah. And then, I'm going to give you an example. So, again, this is not exam. What is this? This is called combinatorial proof. So, how you prove this kind of thing? There are 2 ways. Number 1, you do the stupid way. You write down the math and you work very hard to prove this is true. Or you do the smart way. Smart way is you do logic by this. How do I prove this is true? How do you prove this is true? So you can prove it mathematically by what? Write down 4 factorial, divide by 2 factorial, and then do all the stuff and try to show this is true. But that will take you 10 pages. Here's the crazy way. What the meaning is this? The meaning is you have a bag of 4 N balls. You pick 2 balls. Okay. Now what is this? This is what makes combinatorial interesting. You assume among these 4 N balls, 2 N of them are red, N of them are blue, and N of them are green. So how many balls you have? 2N plus N plus N, 4N. And now you pick 2 balls from this red, green, blue thing. Then you have following combination. What is this? Some rule. You either pick the 2 balls, both of them are red, or 2 balls, both of them are blue. The 2 balls, both of them are green. One is red, one is blue. One is red, one is green. One is blue, one is green. And these are all the possible ways you can pick ball. So you sum of them, it gives you this number. And since method 1 ignore the color, but it's the same 4N ball, method 2 I care about the color, it's always the same 4N ball, therefore left equal right, finish the proof. I don't even need to do what is this. I just argue. And what is the argument here? I just consider all the possible cases, so in this case I'm actually drawing a tree. And this is how you prove this kind of crazy thing without using calculation. If you do this, this is the next easy one. What if this one? What if this one? If you do this kind of method, of course you can, but it takes 10 pages. But if you come up with a very smart way to split this 4N ball into 2N, N, N, then you make up this argument, and then they say these are all the possible cases you can get 2 balls, and you sum all of them, and then you simplify a little bit. Yeah, this is exactly what you want. And since you are counting the same 4N ball, so of course they have to be same. Then you finish the proof. So this is called combinatorial proof. Don't worry, no exam. I just let you know this kind of thing exists. And this is how you prove this thing, this thing, this thing. And then, okay, lastly, let me talk about Friday. Everybody will automatically get 100 attendance. And first come, first serve. If you want to come, you come. If you don't want to come, you don't come. I will make the video, don't worry. That's all.